Hello everyone, my name is Lao Kaiyao, and my topic today is about the parallel I/O, which is a multipurpose communication peripheral. Today, I'm going to introduce an atypical usage of parallel I/O, that is, a logic analyzer based on the parallel I/O peripheral. And I'm an embedded software engineer from the IDF chip support team. We are mainly responsible for bringing up and introducing the new targets in the IDF and maintaining the peripheral drivers and also their examples. Personally, I mainly work on the I2S, touch sensor, parallel I/O, DAC, and the analog comparator. Let's begin with a question. How can you monitor the signal waveform if you don't have a logic analyzer? If you only have an ESP chip, then you can take a try with the parallel I/O peripheral. So this presentation will cover these parts. Firstly, let's take a look what is the parallel I/O. And next, I'll briefly introduce the RX driver of the parallel I/O. Then we'll come to the logic analyzer example. I'd like to share three main parts that it consists of and demonstrate how to use this example. Lastly, I believe you are interested in the scenario and the performance of this logic analyzer. So I will conclude with the advantages and the limitations to help you better understand when it is useful. Let's begin with our first part. What is the parallel I/O? In short, it's a multipurpose communication peripheral which has multiple data pins. It is compatible to various bus protocols like I2S, SPI, including DOR, Quad, and even Octo SPI, and the Intel 8080 parallel bus, DVP, RGB LED matrix, and lastly, it can perform as a probe of the logic analyzer, which will be introduced later. Maybe some of you have noticed that the parallel I/O firstly appeared on the C6, so it is relatively a new peripheral in the ESP IDF. Currently, only the last two cases have been accomplished in the IDF example. You can find them in this path, but the other cases are still under development. We now have four targets that support parallel I/O peripheral. They are C6, H2, P4, and C5. To understand the parallel I/O peripheral quickly, let's take a look at the timing diagram. As you can see, it mainly consists of clock, data, and valid signals. And there are some points you need to take care of. The input and the output clock line are separate, which means you can input a clock on one GPIO and then output it on another GPIO. Regarding different chips, there will be up to 8 or 16 data lines available, and one of data line can be used as valid signal, especially this valid signal is optional, and it will occupy one data line if you need it. There is a limitation that the bus width must be a power of 2, like 1, 2, 4, 8, or 16. So if the valid signal takes one data line, then bus width needed to be run down. For example, when there are 8 data lines in total, and one is used as the valid line, then you can only use up to 4 data lines. And to satisfy all kinds of data endings, the bit and byte order are configurable. Let's go more explicitly. For the TX simplex mode, we can enable the data gating and the clock gating to generate different waves. The data gating can decide to send the data continuously or piece by piece. And if we enable the clock gating, the clock line will output the non-free running clock, which means only outputs the clock when the valid signal is active. And the case is different on the RX side. There are 3 kinds of delimiters regarding different valid signals. They are level, pause, and soft delimiter. The level delimiter is actually same as the data gating in the TX direction. The data are only received when the data signal is active. By the way, you can also set the valid signal active on the low voltage or on the high voltage. So the delimiter can be used to receive I2S bus with Phillips and MSB format, as well as SPI and DVP bus. The delimiter can literally separate the data with ports. This timing diagram only shows a typical usage of I2S of the PCM format. It is actually quite flexible. You can choose the ports aligned with the data or has one bit shifted like this. As for the soft delimiter, it is totally controlled by the software. You can decide how and when to start and stop the sampling in your code. Therefore, we can realize the logic analyzer based on the soft delimiter. Now let me give a brief introduction to the parallel I/O RX driver. The parallel I/O peripheral is abbreviated as Palio in the driver. And the driver is consisted of some public headers and private resources. The TX driver and the RX driver has separate headers. You can only include one of them if you don't need another one. In this presentation, I'll only use the RX driver. Okay, let's check what APIs we got in the RX driver. As you can see, it's quite easy. There are only 9 APIs in total. These APIs include the unit allocation, enable, disable, event callback, delimiter creator, and the most important, the transaction. Although they are pretty simple, they still keep enough flexibility and able to work in various scenarios, especially this transaction API. It can support synchronous or asynchronous reading. Also, it allows to receive the data into the internal buffers and then copy them out, or receive the data into the user buffer directly without the internal buffers. And even the delimiter is changeable among the transactions, which means you can receive the current packet in level delimiter, but leave the next packet in software delimiter. Then how does the driver work? Here is a simplified workflow. We can split it into 3 parts: the application, driver, and the hardware. Firstly, we need to initialize the driver. Then, for the asynchronous mode, we need to register the callback to receive the data asynchronously. And then, we can enable and receive the data. To receive the data, the received configurations need to be specified. The created delimiter handle can be attached into this configuration. The receive function will pass the configurations and the payload buffer into the driver. If we want to receive synchronously, here is a block function that will block until all the transactions are done. After that, the driver will pack the configurations and the payload into a transaction descriptor and push it into the transaction queue. The DMA will keep receiving until the current transaction is finished, and then take another one from the transaction queue. When the receive event takes place, there will be a callback from the ISR for the asynchronous mode. And if all transactions are done, it will unblock a synchronous waiting function. And then the received data can be accessed in the payload buffer. Now it's time to introduce the logic analyzer implementation to see how it works. Typically, there are 3 main steps for a logic analyzer, which are sample, transmission, and the decode. We need to sample the data first, and then send them to the host. And finally, the software on the host can help us to parse and decode the data. In this logic analyzer example, the sample part is realized by parallel I/O driver. Meanwhile, it provides flash and TCP stream to transmit the data. As for the decode part, I'll take pulse view with BCD format, for example. So how we sample the data in this example? There are 2 kinds of signals supported. We can sample either internal signals or external signals. The internal signal is based on the GPIO matrix feature. The GPIO matrix allows to connect one output signal and multiple input signals on one GPIO. That means the output signal can not only output the data to the GPIO, but also loop back internally to the input signals. Let me take I2S for example. When we connect the I2S output signal like BCLK and parallel input signal data 0 on the same GPIO, the BCLK signal can output to the GPIO normally, and meanwhile it will also be received by the parallel data 0 signal. If there is an external signal input like I2S data in, it will be received by both I2S SD in signal and the parallel data 3 signal, so that we can realize the self-probe without affect other peripherals. As for the external signal, we need to connect to the probe GPIOs with the target and sample the data via these GPIOs. Aside of these two signal sources, the example also provides two data modes and two I/O streams. As most of the logic analyzers support both of the buffer mode and the stream mode. This example is no exception. Stream mode will send the sampled data timely until stop sampling, and the buffer mode will save the data to the RAM first and then send them later. The main differences are listed here. Briefly, stream mode relies on a fast and stable transmission. Meanwhile, the buffer mode requires a large RAM size. Due to the limited bandwidth in the embedded system, we can sample for a long time in the buffer mode. Nevertheless, the buffer mode is still more stable than the stream mode. That's why it is more recommended. And next is the I/O streams. I believe you can come up with many I/O streams. Here I just listed some of them. Currently, this example only implemented the TCP stream and the flash stream, which are more compatible among these targets. As you know, the most typical I/O stream for a logic analyzer is USB, but it is not realized yet. Third part about the decode. After we receive the data on the host, it will be dumped into the VCD format. Then we can use the pulse view to open this VCD file, and the data waveform will be displayed. The pulse view is a powerful waveform viewer that supports various decoders and the datasets. You can also select other VCD viewers according to your requirements, like GTK Wave or the VCD project on the GitHub, which is based on the command line. You may ask, what is a VCD format? The full name of VCD is value change dump. It is written in ASC2 format, and it is a part of IEEE 1364 standard. The VCD file mainly consists of these parts. Firstly, the header section, which specifies the info like date and the time scale, and then the variable definition section, which defines the type, bitwise, name, and the symbol for the variable. Thirdly, the dump vars section, which specifies the initial value of these variables. In this example, these variables are all initialized to 0. And lastly, the value change section, which records the value change on a specific time point. Like here, the channel changed to 1 at the 4th point and change back to 0 at the 8th point. Basically, it is a simple format, right? Talk is cheap. Let's watch a demonstration video. In this example, the default sample rate is 8 MHz, and these 4 GPIOs are used as probes. You can train them according to your requirement. Let's take ESP32C6 for example. Firstly, we need to set the configurations in the menu config. Choose the ESP probe configurations. We can set the signal source in the first option. As you can see, we are able to monitor the internal signal or the external signals. The default internal signals in this example are 4 toggling GPIOs. I'd like to show you some bus protocols. So here I choose to probe the external signals. I'm going to burn an I2S example in another target to generate the I2S signals and monitor them by this logic analyzer example. The second option is the dump mode selection. You can just use the recommended buffer mode. And the third option is for choosing the I/O stream. Here we use TCP stream, for example. Then we need to specify the IP address of the host server. Mine is 40 here. And the server port, just keep it at the default. To use the TCP transmission, we also need to specify our network connection. If we'd like to use Wi-Fi, don't forget to specify the SSID and the password here. Okay, that's all for the configurations. So let's burn the I2S example first. Okay, I2S is running. Back to the logic analyzer example, we need to start the TCP server on the host first. As we mentioned before, there are 4 probes, so there are 4 channels here, and the following output file name is optional. After the TCP server started, our preparations are done. Let's burn this logic analyzer example. The example will connect the Wi-Fi first and probe data automatically. You can see all the data are received and the TCP server is closed. Let's check the output VCT file. Yeah, the data has been transferred into VCT format. Then we can open it with the pause view. Here, we import with VCT data. We got 4 channels. Let's zoom in. You can see the sample points on the waveform. Then we can add the I2S decoder to pass the data. We need to assign the channels for the I2S decoder. And then we got the data in each slot, which are exactly what we sent from the I2S master. Okay, because of the time limitation, not all modes are shown in this video, but you can refer to the README of this example for other details. Okay, it's time to conclude this logic analyzer example. Comparing to other typical logic analyzers, this solution is cost-effective, especially when we use it for the self-probe. And as an ESP solution, we are able to monitor the data remotely by Wi-Fi. Also, it is software triggerable, which means you can customize the condition of how to start and stop the probe. For example, it can be used to log the signal wave when some errors occur. However, there are also some limitations. The sample rate is limited by the clock of the parallel I/O peripheral, so it cannot achieve a very high sample rate. And limited by the small RAM size, we can only sample in a short time. You might ask, can we save the data to an external PS RAM instead? The answer is yes, we can, but please take care of the actual writing speed of the PS RAM. It should be faster than the sample data produced. This table contains the performance and the capability of these chips. Firstly, I have to clarify that these data are not measured from a strict environment, so they can only be taken for reference. As you can see, the maximum sample rate is about 80 MHz. So theoretically, the max throughput is about 160 megabytes per second. For the buffer mode, you need to take care about the sample time. Here, I calculated a sample time for example. It is dependent on the available RAM size, the sample frequency, and the bit width. If we only use the integrated SRAM, the sample time will be about several milliseconds. Here is about 6.4 milliseconds. As for the stream mode, it is heavily dependent on the hardware and the network environment, so please pay attention to throughput rate. As a relatively new peripheral, the parallel I/O still got some work to do. Some of you may be thinking, there are too many steps to use this example. It is inconvenient at all. Yes, that's true, but I believe it will be easier to use when it can connect to the pulse view with USB directly. Apart from the inconvenience, there are only 2 I/O streams available for now, so later we'll support more streams to satisfy different requirements. Okay, that's all for this presentation. Hope it is helpful and inspiring to you. Thanks for watching, and any questions are welcomed.